Day 5, we look at the box problem in class. We design open-top boxes and we figure out which one has the biggest volume. And we do that just by modeling. So we actually make the boxes in class, but then we do it mathematically as well. So everyone gets a piece of printer paper, which is 21.5 by 28 centimeters. We cut out boxes from the corners and fold it up to make a 3D box. To find the volume of a box, so again, we had a box that looks something like this, with an open top. So we had a piece of paper and we just cut out the corners and we folded up the sides to make these boxes. So then I had every student measure the length, the width, and the height to get the volume. So again, volume equals length times width times height. And we found in each class who had the largest volume and what size was the box that they cut out from the corners. So the question, how could we calculate the largest square we could cut out from each corner, so these squares right here, to obtain the box with the largest volume? And then what does this have to do with higher degree polynomials? And that's the mathematical part that we looked at in class. So here is how you do it mathematically. Again, we start with this piece of paper that's 28 centimeters this way by 21.5 centimeters this way, but we cut corners, so each of these corners we cut out that are x by x boxes, and we wanted the volume of the box that we created when we folded those up. So we had to figure out the length of this right here and this right here. And so to figure out this first red line right here, we knew that it was 28, but we're taking out two of the x's. So again, volume equals length times width times height. So in this case, volume equals 28, but then minus the 2x. So that would be this side. And then to get the other side, to orange, right here, that would be 21.5 minus 2x. And then if we folded up the sides right here, the height of this box, this open top box, would be x. So there's the length times the width times the height. How do we find the zeros of this equation and what do they mean? And so we talked about in class, if you want the zeros of something and you don't know what they are by looking, you can make an equation, set it equal to 0. So we have 28 minus 2x. What makes that equal 0? We can solve it algebraically. We can subtract 28 from each side. We get negative 2x equals negative 28. We can divide each side by negative 2. And so when we do that, we get x equals 14. There's one of the zeros. Let's do that over here for this problem right here. We have 21.5 minus 2x. We want to know what makes that equal 0. So we'll subtract 21.5 from each side. We get negative 2x equals negative 21.5. We'll divide each side by negative 2. So our other 0 is 10.75. And then the last one, we have just x. So if we plug in x equals 0, that would make the whole thing 0, and that's a 0 as well. So it says, what does that mean in this situation? What's the domain of the function? What possible x values can we cut out of the corners of each of these? And so the zeros deal with the domain. If we cut out corners of 0, if we don't cut anything out, we can't fold it up and make a rectangle. So we know that what we cut out has to be bigger than 0. So we can say, all right, x has to be greater than 0. But if we cut out 14 from each side, so again, this side was 28 inches. If we cut out 14 from each side, there will be nothing left to fold up. So we know we can't cut out 14. Likewise, over here, half of 21.5 is 10.75. And if we cut out and remove the middle of this and the middle of this, there's nothing left to fold up. So we cannot cut out sides of 14 or 10.75. When we're writing the domain then, it makes sense that the largest that we could cut out would have to be less than 10.75. If we cut out anything bigger than 10.75 from each side, that smallest side would not fold up. So the domain in this situation talks about what you can cut out from each side, and that number would have to be between 0 and 10.75. Anything bigger, and there'd be nothing left to fold up. So next step, let's multiply this equation out so it's in standard form. And the equation I'm talking about is this volume equation. So we're going to multiply that out. In last unit, we multiplied out these things that have three factors by multiplying out any two factors first, and then taking that answer and multiplying by the third factor. So I'm going to use a box and multiply out the 28 minus the 2x, and we're going to multiply that by that 21.5 minus 2x, and we're going to get the inside right there. All right, so 21.5 times 28, that's 602. Negative 2 times negative 21.5, that's negative 43x. Negative 2x times 28 is negative 56x. And negative 2x times negative 2x is 4x squared. All right, let's write that in standard form. We have 4x squared minus 99x when we combine like terms, plus 602. All right, now we have to take that and we have to multiply by the height of the box, this last x here hanging out. All right, so let's multiply by x. And when we do that, we get 4x cubed minus 99x squared plus 602x. Here's the equation. We will put volume equals. As a higher degree polynomial in standard form. And so in class we talk about what will the shape of that graph look like. So we know it's a degree 3 graph and the lead coefficient is positive. So if we were to graph that, it should be a bendy straw graph and you're drinking up the straw because of the force. So we know our graph might look something like this. So now in our graphing calculator, we're going to type that in and I tell you how to change the window. So I'm going to type in, I'll pull this up, the 4x cubed minus 99x squared plus the 602x. We're going to change our window and we're going to figure out what does this have to do with cutting out the squares and finding the volume of the box. So it takes a second for this to pop up. Okay, so we'll type in 4x cubed. So let me open a graph page, or you can use the calculator scratch pad. I'll just use the calculator scratch pad. Okay, so we have 4x to the power of 3, arrow over to get down, minus 99x squared plus 602x. When we hit enter, we won't see the whole graph, so I say, all right, change your window, menu window zoom. Let's go from negative 2 to 20, and we should be able to see it, and negative 3,000, and I just played around with this earlier to get the window that fit to 3,000. Okay, and we can see that bendy straw graph that's increasing. So if we want to know the maximum square that we can cut out in the maximum volume, it makes sense we're looking at the maximum point that we can see. Call that the local maximum. So we're going to go to menu, analyze graph, maximum, go anywhere to the left of your max, to the right, and here it is. And remember, the x value is what you can cut out. So if we cut out squares of 4.02, we will get a max volume of, and this is e to the 3, it means move the decimal place over 3 times. So we'll get a max volume of 1,080. So let's write this down. So again, on our graphing calculator, we found this max point was 4.02, 1.08 E3. And the x value is what we cut out. So what should we cut as the x value? And that's 4.02 centimeters. And the greatest volume is like plugging in the 4.02 into the equation and solving for y. And it's 1.08 E3, which is scientific notation, which means take that decimal and move it over 3 places. So that's 1,080 centimeters cubed for volume. All right, so that's how you can use a higher degree polynomial to find maximum amount we can cut out and maximum volume.